Okay, so today we will we'll look at another example where we are looking at a case where a motor is operating in a leading power factor. So just to show you how the phasor diagram is basically drawn and how can you analyze the salient pole machine when it's operating in motor mode in leading power factor. All right. So you will see in example 4, you've been given the D and Q axis synchronous reactances, and you've been given the power factor of the motor, and also how much of active power per phase is the machine absorbing from the line. Okay, and it's also operating at rated terminal voltage. So using the data provided, we will draw the phasor diagram in per unit, and we will basically work out the total power that is due to the field excitation and also due to the saliency. Right. So as they've basically defined in the question is your active power drawn in this case is 0.8 per unit. So using your formula for the active power drawn by the motor, so P is equal to EI cos phi, we can determine we know that the machine is operating at rated voltage, so it will be 1 per unit. The power factor is 0.8, so we can replace that. So, and we know the active power is 0.8 per unit. So using this equation, remember that they've given us the active power per phase. So I've basically written the equation in power per phase here. Okay, so we know we don't have 3 there, which will indicate 3-phase power. Here it's power per phase. So using your active power equation per phase, you can determine the current. As you can see, if your power factor is 0.8 and the power is 0.8, that basically produces a current of 1 per unit being drawn. So that's basically a full load current being drawn by the motor from the mains, right? And using your angle for using the power factor, you can determine the angle phi. Okay, so it's leading, so the angle is positive here. And also we can write the terminal voltage also in per unit. And as you know, it's the reference phasor. Right, so as we've discussed in the someone needs to mute there. Trimira, you need to mute your microphone, please. Right. Okay, so from the equation that we discussed in the notes, right? So we have 4 cases, and that led to 4 different equations depending on the mode of operation of the machine. So this is the equation we've basically derived when the machine is operating as a motor in leading power factor. So using that same equation, you can basically substitute the values for the terminal voltage, the current, and cos of phi and sine of phi. You can determine that one, and also the Q-axis reactance. And using that, you can determine the angle at which the motor is operating at. So that's the angle delta. Okay, and again, this equation we've shown that in your notes. The terminal voltage, which is E, cos of phi. So when we resolve that vector and we add this component, which is I dxt, on your phasor diagram in your notes, you will find that you end up with this induced voltage E naught, and we can also further simplify this equation with the data that we have basically at hand, and that's basically writing ID, which is the current along the d-axis, in terms of the current I, which is your current that's absorbed by the motor.
Sorry, sir.
So, yes.
So I don't quite understand how E naught is equal to E cos this angle and I dx. Can you please explain? I didn't quite get it even in the notes. I tried to find the place where E naught is equal to E cos of this phi plus I dx.
Okay, I will just open the notes first so that we can go back to that phasor diagram. Right, so we're looking at the case where the motor is operating in leading power factor. Okay, this is the case here. Can you see the phasor diagram?
Yes, sir. Yes, sir. I can see the phasor diagram.
Okay, thank you. So, as you can see here, this is your phasor E naught here, right? So that's the induced voltage that is behind your terminal voltage. And when you want to work out this phasor, right, if you project, as you can see there, I've projected a perpendicular here, right? So meaning that this phasor E here, when you resolve it using angle delta, so this component from this point to this point here is E cos of delta, okay? So E cos of delta will give you this, this portion here. And then from this point here to this point, you basically have, as you can see, parallel to it is I dxt. Okay, so that's what I've written in the equation there. So I said E naught, the full phasor, is this section here, which is E cos of theta, plus this section here, which is I dxt, right, from here to here. So if you look at my solution here, I've written the same thing here. I said E cos of delta plus I dxt. Is that clear?
Yes, sir. It's clear now. Thank you.
Okay, thank you. Right, so I've basically further expanded ID to be I sine phi plus delta. Again, that's from the notes. And basically, we are basically replacing this current in terms of those two angles here. And then basically we end up with all the different parameters that we have basically worked out so far. So we know what is E, the terminal voltage, we know what is delta, we know what's I, xt, and then phi plus delta, we can work that out. So we can substitute here and work out the value of E naught. Okay, so that's your induced voltage per phase in per unit, and we can write it in phasor form. So in vector form, sorry, and that's basically the magnitude and the angle. And as you know, in motor mode, your induced voltage is a lagging phasor with respect to the terminal voltage. So remember, you need to put a negative sign here, right? So from there, you can basically, we worked out all the different values there for the phasor diagram. So I've drawn the phasor diagram for a leading power factor salient pole motor, right? So as you can see, we start with the reference. That's your phasor E, which is the terminal voltage, and then I've basically drawn the induced voltage E naught, and that's your current, which is a leading current at a certain angle phi. and I've substituted there all your values, inserted your value of phi and delta, and also worked out what is ID and IQ there. Okay, so remember that to get IQ and ID, you need to use the sum of phi plus delta, okay, to get ID and IQ. And then I've also worked out the drops across the two reactances. I'm sorry, there's a small, that should be XD here, so it's ID XD and then IQ XQ here. So please correct that. It's ID and not it's ID XD and not ID XQ here. Right. So this is how you basically draw your phasor diagram for a salient pole motor in leading power factor mode. And as I said, you have to make sure that all the values are inserted, all the phases labeled, and also you insert all the values for each of the phases. Okay. If you're asked to draw a phasor diagram in your test, you have to make sure all the values are inserted and the units and the angles, so that each phasor is basically represented properly with its magnitude and its angle. Right. So once you've drawn the phasor diagram, the next part is to, as they've asked, is to work out the portion of the power that's due to the field excitation, and the second part due to the saliency. Okay, so we'll use the equation that we've been given for the two different portions. One is the total power that's due to the field excitations. So here we use XD, right? And we are working out the three-phase power here. So I've multiplied by 3. Okay, so it's not the field power per phase, it's the total. When you say total, then you take it as 3-phase and you multiply by 3. So it's E naught sine delta of XD times 3, and that's your power due to the field. And the second part, that's your second part of the equation, which is for the salient part. So it's E squared over 2 times 1 over XQ minus 1 over XD sine 2 delta. So again, you insert all the values and work out the value here for due to saliency. And also again, I've multiplied by 3 there because it's 3-phase. Okay, so this is how you work out the power due to the field excitation and the saliency. And if you add both, you will get the total 3-phase power that the motor is basically producing. Okay, that will be the total power that the motor is producing. Any question on this analysis? Okay, so I will basically move to the next part. We have a more complex question, which I will basically upload on the Moodle page. This is a tutorial question where now I've basically inserted the stator resistance in your salient pole machine, and we will show how, when we are given, how can we basically represent the stator resistance on the phasor diagram and draw the full phasor diagram with this stator resistance represented. So you will see that in this question, the data that will be provided, it is slightly different because now we have to work out the armature resistance voltage drop. Okay, so that's the drop across your synchronous resistance, okay, or armature resistance. So they've provided you with the power factor of the machine. Okay, it's operating as a generator at rated terminal voltage and current. So when they say rated terminal voltage and current, if you're writing it in per unit, both of them will be 1. Okay, so that will be the terminal voltage E will be 1 per unit, and the current is also 1 per unit, okay, when it's operating at a rated value. And the power factor is 0.8, lagging. And you've also been given the angle between the stator current and the excitation voltage, okay? That's 60 degrees. And you've been given the magnitude of the excitation voltage, right? So that's E naught is 2 per unit, and the armature, that resistance drop is 0.02 per unit, right? So so using the phasor diagram here, we will determine the currents, which is ID and IQ first, and the angle delta. And from there, we will determine what is the direct axis and quadrature axis reactances, which is XT and XQ in per unit. And so normally these values are given to us in the question, but here they've given us the voltage drops, and then we have to work out the reactances. And also in the next part, we will reverse the operation of the machine into motor operation, and we will basically determine the excitation voltage for the motor and draw the phasor diagram. Okay, so it's a little bit more different in the way that we will analyze the machine. Just 1 second, I'm trying to. Right, so just please let me know if you can see the screen now.
Yes, sir. We can see the screen.
Okay, thank you. Right, so this is now this question where, as I said, we've been given the this value, which is the drop across the stator resistance. So we've been given the power factor of the motor. We can determine phi, and we've also been given the angle delta, right? So that's given to us. Sorry, it's the sum of phi plus delta. Okay, so the angle between I and let's go back here. So it's phi plus delta. That's basically 60 degrees here, right? So using the data provided, okay, I've worked out the angle delta. Okay, since we can work out what is phi, and we know that the sum of phi plus delta is 60 degrees, so we can work out what is delta. Okay, so they've given us this angle here, basically the angle between the induced voltage, right, and the stator current, right? So this angle basically is for a generator which is operating in lagging power factor mode. It's the sum of phi plus delta, right? So now using the data provided, we know that we can write ID and IQ in terms of the stator current, right? Remember that it's just resolving this phasor here, right? So IQ will be basically this current, and you resolve it using the angle here, so which is phi plus delta, right? So it will be cos phi plus delta will give you IQ, and I sine of delta will give you ID, right? So that's the adjacent phasor, and that's the on the opposite side. It's using the sine function. Right, so inserting the values, we can work out IQ and ID in per unit, right? And as you can see, I've basically drawn the phasor diagram using the data provided. So this was given, E naught is 2 per unit. And what is important is the way you show the drop across the stator resistance, right? So as you can see, I've basically resolved this drop into two components, right? One is the drop across the resistor due to the current ID, and then the drop across the resistance due to IQ, right? So here you have to be careful because the way we used to represent this resistance initially was it's parallel to I, which is your current, the stator current. So that same phasor is basically is around here, but I've basically resolved it into two components, which is ID and IQ. And as you can see, when you draw that drop due to ID, it has to be parallel with ID. So ID RS, and you will see that IQ RS is parallel to IQ, right? So these are the two components. So when you work out those two components, this is how I've worked it out. So IDRS, you just basically replace ID with I cos of phi plus delta times RS, and you can work it out, the value of IDRS. And again, I've replaced IQ with I sine of delta as phi plus delta, and that gives you the value of IQRS, right? And so those two values are the ones that I was saying here that had worked out. Okay, so that's IDRS and IQRS. Okay, right. So again, if you look at the phasor diagram, right? So you find that we have to get E naught. Now the equation is a little bit more complex since we are representing the stator resistance. Okay, so I've basically dropped a perpendicular here, right, from this point here, perpendicular basically with respect to IDRS. Okay, so to get E naught, now you need this phasor here, this part. Okay, so this part is the resolving this phasor, which is E and then cos of delta, right? So from here to here, this portion is E cos of delta, right? And then we need to work out what is this portion here from this point here up to here, right? So this is basically this section here. Okay, so as you can see, it's got two components. It's got IQRS and IDXT, right? So this section here. So I've written this full equation here in the next part. So E naught is E cos of delta IQRS plus IDXD, right? And from there, I've basically made XD the subject of formula and then solve for XT there. Okay, so because we know what is E naught, what is E cos of delta, and IQRS and ID, so I substituted the values and then you can work out what is XT. Okay, so this is how you get the D-axis reactance. And for the next part, you can see there I've written E sine delta, then it's IQXQ minus IDXT, right? So let's go back to the phasor diagram. So here I've drawn a parallel line here, okay, to this phasor here. And as you can see, I've splitted this section, right? So this vertical here from here to here basically is the opposite of resolving this phasor E naught here, sorry, E along the vertical, right? So this section here will be basically, as I said, the adjacent is E cos theta. So your one that this from this perpendicular here, it will be E sine delta. Okay, so from here to here is E sine delta. Okay, and then you need to add this portion here, right? So E sine delta is basically this portion. So E sine delta will be, if you take this full phasor here, so that's IQ XQ. Okay, so this is parallel to this here, right? So as you can see, ID XD is opposite to this part here. It's basically subtracting here, right? For you to get this small section here, which is E sine delta, you take the full phasor, which is IQ XQ, and you minus this small portion here, and that small portion is IDRS. Okay, so that's what I've written here. So E sine delta is IQ XQ minus IDRS. Okay, so the reason why we're writing it in terms of IQ XQ is we want to determine what is IQ here. Right, again, I've made XQ the subject of formula, and then I've solved for this reactance XQ. Okay, so that's your quadrature reactance of the machine. Okay, and that's the full phasor diagram for the generator operating in lagging power factor mode. Do you have any question?
No, sir, everything seems clear.
All right, thank you very much. Okay, so in part B, they've asked us to now reverse the operation of the machine from generator to motor. Okay, so the data provided is, let's have a look here. So they said the motor is operating at rated terminal voltage and leading power factor at 0.8, and we've been given the load angle, right? So we know what is delta, and we asked to basically work out E naught. Okay, so provided we know what is the power factor and the angle delta. So if you look at your notes, this is the structure of the phasor diagram for a leading power factor motor. And as you can see, an important angle you need to work out is the sum of phi plus delta, right, for this machine. And so you need to add 36.87 to 30 to get this part, which is 66.87, right? So that's the summation of delta plus phi, and that will enable you to determine those two currents, right? So those two components here, which is IQ and ID, can work it out using this the sum of those two angles. So I cos of phi plus delta and I sine phi plus delta, you'll get the two values, right? So the next part, you will see that now with the representation of the stator resistance on the phasor diagram, the equation has changed, right? So the equation for E naught is slightly different now compared to when we neglect the stator resistance. Okay, so as you can see, when you start with E naught and then you have IDXD, which is similar to what we've worked out in IQXQ. And then what I've done is I've added two components here, right? So one is IDRS, which is basically parallel to ID, right? So that is basically added to this phasor IQXQ here because it has the same direction. And Then the other phasor, which is parallel to IQ, right, will act basically in the same direction with E naught, right? So that's IQRS. So those two components now, when we add them on the phasor diagram, it changes the equation, right, for your to determine E naught. Okay, so in the initial case, when we were neglecting the stator resistance, your value was of E naught, as I explained earlier, it was basically E cos of delta, then you added only I dxt there, right? So that was the initial way of working out E naught. But now, as you can see, E naught is basically this full, you add E cos of delta to get this section, and then you basically need to add only this portion. And how you get this portion is you take the full phasor, which is I dxt, from this point to this point, and you extract this part, which is IQRS. So that's what I've done here. So E naught is E cos of delta, and you take I dxt and minus this part, which is IQRS, and that will enable you to determine this portion, this drop, which is basically IQRS. You need to determine that part and then subtract it there to get E naught. Okay, so the value of E naught comes out to be 1.995, and the next okay, yeah, so we don't need to work out the power for this case, but you can work it out on your own if you wish. You can work out the power due to the field and the saliency because you've got all the data that's needed there. All right, so that was for question 1, which is basically representing the stator resistance on the phasor diagram for a generator and as well as for a motor as shown here. Okay, so as you can see, the analysis is a little bit more complex because we're adding those two components here, which is IQRS and IDRS on each of the phasor diagram. But what you need to understand is, remember that these two drops are always parallel to the currents, right? So IQRS will be parallel to IQ and IDRS will be parallel to ID. Okay, so just to get you going for, I will basically post this on the Moodle page because I will stop at 9:25. So we will look at the next question here for the next session. So in the meantime, maybe you can just give this question a try. Question 2 on the tutorial. It's a basic salient pole synchronous motor where you're given the reactances of the d-axis and q-axis, and you are also given the operating point of the motor. So it's operating at rated current, so it's drawing 1 per unit, and the power factor is 0.8 lagging, right? And you've been given the rotational losses, and from there you can you're asked to work out the excitation voltage and draw the phasor diagram, and then we will be required to work out the power per phase due to the field and also due to the saliency, right? And next part is if the field excitation is reduced to 0, okay, you have to determine whether the motor will stay in synchronism with the line or will it lose stability, right? So that will determine, that can be determined from whether your angle at which the motor is operating, whether it's greater than the maximum angle that the motor is allowed to operate. Okay, so you'll have to determine that. And the last part So if you remove the load from the motor before the field current is reduced to zero, meaning that you are still providing field current to the motor and you just remove the load. So you're asked to determine whether the resulting current drawn by the motor, what will be this resulting current that's drawn by the motor, and also to draw the phase diagram for this operating condition where you have basically removed the load from the motor. Okay, so I will post this on the Moodle page. You can just give it a try, and then we will go through the solution in our next session.
So,
okay, guys. Yes.
can you please go to the solution of the example? I have a question on example 1.
Example 1.
Yes.
Okay, 1 second. Yes, that's example 1.
Scroll down a little bit.
Yes.
Once more. Yeah, so how did you get this in the vector of E naught line to line to be 4,508? I didn't get it. How did you get it?
So for you to get the voltage, firstly you need to determine the base value, right? So you need to determine EB,
Yes.
right? So when you multiply E naught by EB, you'll get the value in volts, right? So you're converting the unit from per unit to volt. And then now the line-to-line value will be different from the phase value, okay, depending on the type of connection of the motor. So there'll be the factor of √3 that comes in. Did you check that?
No, I forgot.
Yes. So there are two things. There is EB and there is √3 that you need to consider to basically determine your line-to-line value.
Okay, thank you, sir.
Okay, sure. Okay, guys, so we'll meet in the next session. Just attempt question 2 in the tutorial, and then we'll go through it in the next session. I will basically in per unit, and we'll look at question 2. As I said, it's operating at rated voltage, and it's also operating at rated load, which means your current is 1 per unit. And your rated terminal voltage is 1 per unit, and the angle of the terminal voltage is 0 degrees. That's your reference phasor, and the angle of your current is 36.87 positive, which means you have a leading current. Oh, my bad, that should be lagging. It should be minus there. Just correct that, please. Okay, so let's confirm this. So they said it's drawing lagging. Yes, correct. It's lagging current, so this should be minus there. Right. So from your notes, for a lagging power factor motor, we've derived this equation. Tan delta is I xq cos of phi over E minus I xq sine phi. So from the data provided, we can determine what is cos of phi and sine of phi. And also we've been given the q-axis reactances. So we can substitute and get what is the angle delta for this machine. And since the motor is operating in lagging power factor, the angle of interest will be basically phi minus delta, right? So also this is based on the phasor diagram of the lagging power factor motor. and basically we use phi and delta and get the difference, and that angle, we're going to use that to basically determine the two currents ID and IQ. Okay, so remember that IQ will be along your induced voltage and ID is perpendicular to IQ. So using those two angles, we can determine ID and IQ, as shown here. Right, so from there, if we look at the phasor diagram, we can see that in order for us to determine the induced current, we're dropping a perpendicular from so from your induced voltage, a perpendicular which is parallel to IQ XQ, and that is basically, if we resolve this phasor, which is E along E naught, we get basically E cos of delta up to this point, from here up to here, that's E cos of delta, and then this small portion here is your phasor IDXT, right? And so in order for us to get E naught, right? So what I've done is, okay, just let's confirm this. Right, so okay, so when we resolve E along delta, we're not getting this portion, we're getting the full part here. So from this point to this point is E cos of delta, right? And for us to get E naught, we need to subtract this phasor from there. So E cos of theta up to here minus I dxt, which I've done here, you get basically E naught, right? So I've worked it out. So that's your value of E naught, and the angle is minus 22.84. Okay, so that's from the angle delta that we worked out using tan delta. And from there, we can determine the induced voltage in vector form. And also we can draw the phasor diagram and insert all the values. So just take note, we have two angles to show. One is delta and one is phi. Then we have to basically work out ID and IQ. I is 1 per unit. And then we have to work out IQ XQ, the drop across your Q-axis reactance, and then IDXT, the drop across the D-axis reactance, and also work out then the value of E naught. So all the values are inserted and all the angles are inserted in the phasor diagram. And also don't forget the right angle angles between IQ, XQ, and E naught. Right, so this is the first part of the question, right, which is pretty much straightforward. It's basically just a motor that's operating in lagging power factor mode. And the second part is to determine the power per phase for the field excitation and the saliency. So we're going to use the formula for the field excitation and the one for the saliency. Separated them here, and those two formulas are used to determine the power per phase, right? So if you are asked the power, the total power, then you need to multiply by 3. But if it's power per phase, then you just take the formula and basically solve for field power and the saliency power. Okay, so that's for part B. And for part C of the question, so they've given us a situation where the field excitation current is reduced to 0. Okay, so what you need to understand is when your field current is reduced to 0, what happens is your field power will basically drop now, right? So you won't have that power that's due to the field excitation. So if you look at what the total power is prior for the load to be removed, or sorry, for the field current to be dropped to zero, you can see that when you add those two components, the field power and the salient power, you're getting a total power that the motor is delivering is 0.8003 per unit, right? So that's the power the motor is delivering. And now if we drop the excitation current to zero, what happens is we're gonna have only the power due to the salient portion. Okay, so when that happens, right, we can work out what is the power due to the salient portion. So as you can see here, the salient portion is worked out as this is 1 per unit, and with the we've substituted xq and xd in the formula, right? And sine 2 delta. So here we've taken the maximum value, which means that 2 times 45 is 90 degrees, right? So you end up with a sine of 90 degrees to be equal to 1, right? So you're operating at the maximum salient position. And at that position, you can see the salient power is 0.625, okay, which is different from what we worked out before. Okay, so at this position, so the question they asked us is, when your field excitation is reduced to zero, and they're asking whether the motor will stay in synchronism. Okay, so which means that they want to know whether the power that you are supplying to the load is not exceeding the maximum power that you can deliver due to the salient effect of the motor. So maximum power that the motor can deliver is 0.625 per unit, and you can see now the load that's on the motor is 0.8, which is exceeding that value, right? So since your output power is more than the maximum power that the machine can deliver without any excitation, basically then your motor will lose stability, right? So it will lose synchronism with the supply, okay? And it will basically trip off your motor from the line. Okay, so that's for part C. If we look at part D, so they've asked us that if the load is removed before the field current is reduced to zero, right? Determine the resulting current drawn by the motor and the power factor. Okay, so let's look at this particular situation. Right, so if your the shaft load is removed prior to reducing the field current to zero, what happens is your output power will be only supplying what we call just the rotational losses in the system, right? So if you can see there, I've equated output power to be equal to this rotational loss, which is 0.15 per unit, right? And now if the field current now is reduced to zero, basically what will happen is only the salient portion of your power will basically supply this rotational loss, and we can solve for the angle, right? So I've substituted the values in the equation and solved for delta, and as you can see now, the delta is 6.943 degrees. Okay, and when now you drop the excitation current to zero, basically you want this value of you can see on the phasor diagram here, we will only have basically IDXD, right? And this portion, which is E cos of delta, right? So if you look at this phasor diagram here, when you drop the excitation current to zero, what's left in the motor is basically the current drawn, okay, to supply this rotational loss. And when we resolve this, we have basically this phasor diagram looking like that here. So you have basically IDXD that's acting here, and that's IQXQ, and that's your terminal voltage. Okay, so this is how it looks like without any field current in the machine. And if you resolve this phasor here, so terminal voltage resolve along the angle delta, you'll end up with E cos of delta being equal to I dxt. So that's what I've written here, right? So I dxt is equal to E cos of delta, and you can solve for ID, and also you can work out what is the current IQ. So here I said that, as you can see, the vertical component is IQXQ. So E, basically sine of delta, will be equal to IQXQ, and you can solve for basically IQ, right? So once you have the two currents, ID and IQ, you can work out the resulting armature current that's being drawn by the motor, right? So using ID and IQ, and also, as you can see there, I've determined the angle that's basically the angle phi, okay? So this angle between I and basically your terminal voltage. So tan phi is basically the ratio of ID over IQ, and I've solved for this angle, right? And as we know that the motor is delivering a power of 0.15 per unit. So I've also equated EI cos phi to be equal to 0.15 and solve for the angle phi. Okay, so as you can see now, when you take the difference between phi and delta, you end up with 76.31 degrees, and hence basically what it's telling you is the motor is operating at. So you take you can determine the power factor of the motor. Okay, so taking the angle there, which is basically 83.25, we can use that to determine that the motor is operating at a power factor of 0.175 and at lagging in lagging mode, right? So this is how you draw the phasor diagram when the motor basically has lost its field current, and you only end up with the two components, IDXD and IQXQ, and E naught now is basically zero, which is your induced voltage. Okay, so this was the last part in question 2, and we'll look at a last case where now I'm basically showing you how you will analyze a machine that's operating at unity power factor. Okay, so we haven't looked at that case at all in our previous examples and tutorial. So in the last question, we're looking at both cases, one in motor operation of the Salient pole machine, and also we will repeat it in generator mode, just to show you how you go about drawing the phasor diagram and working out the excitation voltage when the machine operates in unity power factor. So when it's operating in unity power factor, the obviously your angle of the current is zero, right? It's in phase with the terminal voltage. So this is how now your phasor diagram will look like. Okay, so you will resolve the current I into two components, one along E naught to get IQ, and then that's your current ID perpendicular to IQ. As you can see, this is in motor mode where E naught lags the terminal voltage, and you will have two components. One is IQ XQ and one is ID XT there. So adding those two parts, you get basically E, which is the terminal voltage. So for us to solve for the induced voltage, as you can see here, so you will need to take, again, E cos of delta, which will be basically up to here, this point, from here up to here, and then you add I dxt here, right? So that's what I've done. Firstly, I've written the equation for your angle. So tan of delta will be IQ xq over E cos of delta. And you see that the equation reduces to a simple form where it ends up to be I times xq over E, right? And from there you can solve for the angle delta. And so once you have delta, you can solve for E naught. So that will be E cos of delta plus I dxt, right? So using this equation, we can solve for the induced voltage, and also using the angle, we can write the induced voltage in vector form. Okay, so that's how your phasor diagram looks like for a motor that's operating at unity power factor mode, right? So, and also remember how the equations are derived for the angle delta, right? So you always take tan of delta and you take the opposite, okay, divided by the adjacent phasor, which is E cos theta, right? And you can solve for the angle. Right, so moving to the last part. Okay, so they've, sorry, part B, we have to basically compute the maximum mechanical power that the motor can deliver, right? So as you can see, this motor has the power per phase. If you look at the equation, it has two components, your field component and your salient component. So substituting your values that you solved in the part A into this equation, you end up with a power per phase to be equal to an expression like this, which is 1024 sine delta plus 177.72 delta in kilowatt. Okay, so this is what is your equation looks like in kilowatt. And if they ask you for the maximum power, you can equate dP by d delta to 0. So we differentiate this equation and we equate to 0 and solve for delta. Okay, so you can see if you use your trigonometric identity here and you end up with a quadratic equation in terms of cos delta, and using your quadratic formula, you have two solutions. One will fall outside the range for cos of delta because it lies between -1 and +1. So you can reject one of the solution and take the correct one, which is 0.2007, and work out what is delta. Okay. So this is your angle at maximum power, and also we can work out what is this value. Maximum power, you just multiply by 3 there, you're going to get the maximum power for the motor. Okay. So that's for part B. And in the last part, so I'm reversing the mode of the machine from motor to generator mode. And we're going to look at how the phasor diagram looks like for a generator that supplies rated power at unity power factor. Okay, so that's part C. As you can see, this is your terminal voltage, and as the generator operates at unity power factor, you place your phasor I, okay, in phase with E, and then you resolve the current into two components, where IQ will lie along E naught, okay, and ID is perpendicular to IQ, and then you will have your two components, which is IDXT and IQXQ, and adding those two components, you'll get basically E naught. Okay, so you'll find that when you take the ratio of tan delta, you will end up with the same equation which we've done in the previous part for the motor. You'll end up with IXQ over E, and that will enable you to solve for delta. Okay, so we're getting 21.54 degrees. And from this value, we can also solve for the induced voltage. So here again, I'm resolving to get from here to this point here. That will be E cos of delta, right? And then add this small portion here, which is parallel to here. So that's IDXT. And I've solved and got the final value. That's 1503. And obviously you can see that here it's in generator mode, so your induced voltage is leading the terminal voltage, so you have a positive angle for the load angle. Okay, so that's how you determine the terminal voltage, and also you can draw the full phasor diagram determining the two currents ID, IQ, and also the two drops across the reactances, which is IDXT and IQXQ. Okay, and then you insert all the values and also insert all the angles. Okay, so that's what we were required to cover for today. This is basically the three questions that I had in the tutorial. So for Monday, what we will do is we will basically move to the next section of the course, which is we're going to look at what are the one second. So the next section that we're going to look at on Monday is we're going to look at permanent magnet synchronous machine. We will go through the theory part, and then we'll have a tutorial on that section for next week. All right. So if you have any questions on question 1 and 2, you can please ask. Otherwise, what I would advise is you attempt again these questions that we've discussed today on your own, and try and solve and draw the phasor diagram yourself, so that you can basically understand these concepts, so that then you'll be basically prepared to answer questions. All right, so we'll end this session for today, and we'll meet on Monday. Cheers, guys.